Hello students, welcome to our class in solid state physics. In today's class, we are going to see cubic crystal system. Before entering into the cubic crystal system, let us first see what are crystals. Crystals are solids which are having the arrangement in a periodic manner. The atoms in the crystals are arranged in periodic manner so that they have some unique properties. Crystal substances have lot of classifications in it. Now, in today's class, we are going to see a part of crystal system. That is actually 7 classes of crystal systems are available and 14 Bravais lattices are available. In this class, we are going to concentrate on cubic crystal system. This cubic crystal system has got 3 types in it. Before entering into this cubic crystal system, some basic definitions of crystals we are going to project here. Hope you will be knowing about what is unit cell. If you are not, I will tell you now. Unit cell is the smallest unit in a crystal which when repeated again and again develops the whole crystal. Now, I am going to draw the cubic unit cell. This is a cubic unit cell which has got its lattice parameters as A, B and C. See, I have attached the 3 crystallographic axes to the cubic unit cell and I am going to write here the 3 primitives or the 3 lattice parameter distances. That is, from the origin, if I take this particular distance along x axis, this unit is named as A, and along the y axis this unit is B, and along the z axis this particular unit is C. So, these lengths A, B and C are called lattice parameters. Then, what are these angles? These angles are named here as alpha, beta and gamma. These 3 angles alpha, beta and gamma are called interfacial angles. This smallest unit which when repeated again and again in a crystal you get a cubic crystal. Okay. So, these lattice parameters, how they have to be in a cubic crystal system? We have a particular set of values, that is when A, B and C match each other, that is A equal to B equal to C, all the 3 lengths of the lattice parameters are same and the interfacial angles alpha, beta, gamma, all the 3 angles equal to 90 degree, that becomes a cubic lattice. Okay. So, this cubic crystal system has got these unique parameters, that is the lattice parameters A, B, C are same and the interfacial angles alpha, beta and gamma are 90 degree. So, this cubic crystal system, again you have 3 Bravais lattice in this cubic crystal system. We are going to see one by one. So, we are now going to see the 3 lattices of cubic crystal system. One is called SCC, the second one is BCC and third one is FCC. What is this SCC? It is nothing but simple cubic crystal lattice. BCC, that is the short form, it is body centered cubic crystal lattice. And the third one, you have any idea? Yes, and that is face centered cubic crystal lattice. Fine. So, now before entering deeply into this simple cubic face centered and body centered cubic crystal, we are going to see some 4 important definitions in our solid state physics. Okay? So, what are they? First one, you will be knowing about what is atomic radius. Usually an atom has got nucleus at the center and you have the electrons revolving around it. So, the radius of an atom is a measure which is r, which is a fundamental value. Okay. So, what is the next one is nearest neighbor distance. Nearest neighbor distance is the measure which is 2 times the atomic radius. So, if you have an atom here and if you have another atom here, so of course this is the nucleus of the atom. So, from the center of one atom to the center of the next atom, the distance is 2r, and this is the nearest neighbor distance. Got it? Let me see and tell you the next one, which is coordination number. So, what is coordination number? Any idea? You might have learned in solid state chemistry also. Yes, the same coordination number is the number of nearest equidistant neighbors, okay, for a particular atom in a crystal. Okay. So, this coordination number will help you in finding out how dense a particular crystal is. The fourth one, what I am going to say is atomic packing factor. The definition of atomic packing factor is quite interesting. What is it? It is a ratio. Atomic packing factor is given by volume of number of atoms in the unit cell to the volume of the unit cell. So, it is a ratio between 2 parameters. What are they? Volume of number of atoms in the unit cell and the denominator is volume of the unit cell. So, by calculating the atomic packing factor, we can know about how densely a crystal is packed. That information can be got. So, we are going to see each and every crystal system, that is simple cubic, body centered cubic and face centered cubic crystal system, and we are going to find these parameters in this crystal system. Let us do one by one. Polonium is an example of simple cubic crystal. Now, I am going to draw the unit cell of a simple cubic crystal lattice. Hope you will all know to draw a cube. Of course, it is very easy. Okay. In general, in a simple cube, if I draw the atoms in the front face of the cube, they will be touching each other, isn't it? So, if I draw clearly the front face of the cube alone, so hope my drawing will be clear now. If I draw the front face of the cube alone, you can see very well the atoms are touching each other, isn't it? You might be better than me in drawing, yes. So, the atoms are touching each other in the front face of the cube. So, if they touch each other, then what is this? This is nothing but a radius of the atom. What is this? This is the radius of the second atom, and this particular side of the cube is now the lattice constant A, isn't it? So, here we have the relation lattice parameter A equal to 2R here. Of course, you know very well, I told you about the nearest neighbor distance just now. So, the nearest neighbor distance here is 2r. In terms of lattice constant, I can put r as a by 2. So, this is the discussion of simple cubic crystal, isn't it? So, polonium is an example of simple cubic crystal, and here we have found out two parameters. One is nothing but this is the lattice constant, and you have our atomic radius to be a by 2, lattice constant divided by 2. And now we are going to use this in finding out the coordination number and the atomic packing factor. Okay. Now, I am going to show you the simple cubic crystal arrangement. See? So, you will be seeing this simple cubic crystal. See, while making models, it is very difficult to make these balls to be bigger and touching each other. So, while making models, we can make only like this. You can visualize now, atoms are present in the corners of the cube, isn't it? So, how many atoms can you see here? Yes, have you counted? Yes, you can see 8 atoms are there in the corners of the cube. 8 corners are there, no, for a cube. So, 8 atoms you can see. So, this front face only I have drawn here. So, you can see 4 atoms in the front face, but actually these atoms are touching each other. So, this corner atom, you can visualize it as a big sphere, isn't it? This big sphere like a ball, okay. So, this big sphere, this is another ball. So, these two big spheres are touching each other, and this big sphere and this big sphere is also, all the 4, they are touching like this. Can you imagine this? Yes. So, you have this 2 atomic radii, so A lattice constant, and that is how we got this relation. Can you visualize this? Yes, fine. So, this simple cubic lattice, now you just think in your mind, how can you find the coordination number? What did I say in the definition of coordination number? Yes, coordination number is the number of nearest equidistant neighbors, that only I said. So, let us take this particular atom. How many neighbors are there for this atom? So, if you move slowly, this atom is in touch with this atom. This atom is again in touch with this atom. So, with this model, you can see these two atoms are in touch, isn't it? Slowly, this atom is in touch with this atom also. Can you see it? So, this atom, it is in touch with 1, 2 and 3. So, if you have an atom in the left in touch with this, you will be having an atom in the right also, isn't it? So, if you have an atom in touch with this at the back, then you will have an atom in the front also. And if you have an atom in touch with this at the top, you will have an atom at the bottom also. So, how many atoms are there actually in touch with this atom? Yeah, 6. So, 1, 2, 3, 4th one is opposite to this here, 5th one is in the front, and 6th one is at the bottom. Can you visualize it? Yes. So, the coordination number of this particular simple cubic lattice is 6. Okay. So, can we write that now? So, coordination number for SCC lattice is 6. So, here I say it again. So, you have, if I consider this atom, 1, 2, 1 at the back, 1 at the front, 1 at the bottom and 1 at the side. So, totally 6 are the number of atoms touching this. So, you have the coordination number as 6, or the number of nearest equidistant neighbors is 6. So, you know more information now about simple cubic lattice, isn't it? So, simple cubic lattice arrangement of atoms we have seen, and we have seen a relation between what is the lattice constant and the nearest neighbor distance, and we have found the coordination number also. Now, we will move on to the next parameter. What is it? Yes, atomic packing factor. So, let us find out the atomic packing factor. For finding atomic packing factor, so let me have that diagram again. So, this is R and this distance is A. Okay. So, what is atomic packing factor? You might have memorized it by now. So, atomic packing factor is a ratio, volume of number of atoms in a unit cell divided by volume of the unit cell. Isn't it? So, first we are going to find out the denominator. It is quite easy. So, I am going to show you this unit cell. What is the shape of the unit cell? It is very easy, no? You can guess it, no? So, the shape of the unit cell is a cube. Hope you will be knowing the volume of the cube. Volume of the cube, what is the formula for volume of the cube if the side of the cube is A? A is the side of the cube, and of course you know very well that cube has got all the sides to be same. So, the volume of the cube is A into A into A, isn't it? So, my denominator is A cube. Being the side to be A, the volume of the cube is A. So, now we have to calculate the numerator, volume of number of atoms in a unit cell. So, I have to find out how many number of atoms are present in this simple cubic lattice. Okay. While doing that, let me think of this particular corner atom in the cube. This corner atom, and you have to imagine that in a crystal and a simple cubic crystal, say, you can't say that only one unit cell is present in the crystal, isn't it? Only one unit cell is not present in the crystal. What is unit cell? Unit cell is the smallest unit in the crystal, which when repeated again and again, you get the whole crystal. So, you will be having lots of unit cells in all the other directions. So, you have to imagine the same unit to get multiplied in all the directions. So, you imagine this particular atom. Okay. So, this particular atom is shared by how many unit cells? Imagine and tell me, how many unit cells will share this atom? See, you can think that there is one more unit cell here, one on the front, one on the top, one on this front side, this side. So, this particular atom is shared by 7 other unit cells apart from this. So, totally 8 unit cells share this atom. Similarly, 8 unit cells share this atom. So, to imagine this, I will help you telling an example. Okay. Have you seen a Rubik's cube? Kids will be playing with that Rubik's cube, they will be turning it and playing. That Rubik's cube is the best example for this simple cubic crystal. Okay. So, you might have seen different cubes, and those different cubes kids will be playing by turning it all. Okay. Similar to that, if you imagine this particular atom in this unit cell is shared by 8 unit cells. Okay. So, how many number of atoms is belonging to this particular unit cell? Let us do a simple calculation. Okay. So, we have to find out what are the number of atoms in this unit cell. So, let me do it separately and come back to this numerator again. So, a number of atoms in a unit cell equal to, so each corner atom shares is shared by 8 unit cells. Okay, then what is the contribution of this corner atom to this particular unit cell? That means only 1 by 8 of this corner atom is belonging to this cell. The other part is belonging to other cells. So how many corner atoms are there like this? Yeah, you know very well, a cube has got 8 corners. So only one atom is totally present in this unit cell. So a simple cubic crystal lattice has got, even though you can see 8 atoms are not belonging to this cell. Only one atom is belonging to this cell. Okay. So only one atom is belonging to this particular cell. So I have that one volume of that one atom. What is volume of that one atom? Each atom is a sphere. You know very well that each atom is a sphere. So when you think a sphere of radius r, this is an atom. So what is the formula for volume of a sphere? It is 4 by 3 pi r cube. That is a simple mensuration formula. That is nothing but 4 by 3 pi r cube is the volume of one sphere. So if you have one atom, then this will be a small calculation to find out the atomic packing factor. So let us do this calculation now. So 4 by 3 pi r cube. So in here r cube, I am going to do, I am not going to put it as r. I know very well what is the relation between r and a. So here from this I have got a relation r is a. So 2r is a or r is a by 2, isn't it? So I am going to put a by 2 the whole cube divided by a cube. Can you do this simple calculation and tell me what is the answer for atomic packing factor? Yes? Have you done the calculation? Yes. So we are going to see atomic packing factor is for SCC, simple cubic lattice, I get an answer of 4 by 3 pi a cube by 8 and then divided by a cube, isn't it? So a cube gets cancelled and 4 and 8 again gets cancelled, I get only pi by 6. Yes? If you find out for substituting the value of pi as 3.14 and divided by 6, you get around 0.52. So if I convert this atomic packing factor to percentage, you have 52%. So 52% of this particular crystal is only packed. So the atomic packing factor shows you how densely a crystal is packed. But for a simple cubic lattice, it is a loosely packed crystal. Out of 100% if it is packed, then you said it is a dense crystal. Here it is only 52%. So you have a loosely packed crystal. Polonium is an example, I told you already, polonium is an example of simple cubic crystal. Okay. So knowing well about simple cubic lattice now, let us move on to body centered cubic lattice. Body centered cubic. So the name itself tells you the arrangement, gives you a clue about the arrangement of atoms in this crystal. Okay. So let me draw the simple way of body centered cubic arrangement. So I draw it like a model so that you can understand. So you have in body centered cubic crystal, you have the atoms being arranged at the corners of the cube. Apart from the corners of the cube, you have an atom exclusively present in the center of the cube. Of course, that atom is inside the cube at the center of the cube. Okay? So, that is why it is called body centered. Okay? So, you have totally 9 atoms say present in an unit cell. Okay? So, 8 atoms in the corners and 1 atom at the center of the cube. So, how is it arranged? Okay? So, now when you draw a particular face or the front face of the crystal alone, then you can visualize it easily. So, along the body diagonal, so can you imagine, I have drawn a diagonal from the back face of the top corner of the cube to the front lower, that is in the front face, that is at the body diagonal it is called. Okay? And you have the atoms in touch at the body diagonal. You have to be clear that the atoms in the corners of the simple cube were touching each other. Here you have to note it that the atoms in the corners of the body centered cube are not touching each other. Only the atoms along the body diagonal touch each other. So, you have 3 atoms, that is one in the edge or the corner of the cube at the back and one at the front the lower side of the cube and one in the body diagonal. All the 3 are touching each other. So, along the body diagonal the 3 atoms are touching each other. Okay? Of course, you can visualize it. This is R, this quantity is R. So, what is R? You know very well that R is the atomic radius. So, here how many R I have put? Yes, it is 4R, isn't it? So, you know very well that 4R I will write somewhere and I will show you what is this parameter. Yes, what is this parameter? Yes, it is lattice constant A. Of course, for a cube each and every side is A, isn't it? So, what is this diagonal? If this is A and this is A, the 2 lattice constants are A, apply Pythagoras theorem in mathematics. What is this particular distance? Which is the face diagonal. This face diagonal is nothing but root of A squared plus A squared, isn't it? So, root of 2A squared or root 2A, isn't it? So, you have this face diagonal and you have this particular parameter to be A. So, what is this distance? Body diagonal. Again call Pythagoras and you can find it out easily. So, what is this? So, root 2A the whole square plus A square and root of that is nothing but root 3A. So, I will write down here 4R equal to root 3A. So, is it clear how I got that root 3A? So, you know this lattice constant and this is lattice constant. So, you are finding out the face diagonal which is root 2A. Now, taking this face diagonal root 2A and this height to be A, you are finding out this body diagonal to be root 3A. Already you know this is nothing but 4R. So, 4R is root 3A. So, what is the relation between R and A now? So, the relation between R and A is root 3A by 4. Is it clear? So, now you have got an important relation between atomic radius and the lattice constant. Okay? So, R equal to root 3A by 4. Now, if you are asked in some multiple choice questions and all in exam point of view, then what is the nearest neighbor distance in body centered cubic crystal? Do not get panic, it is very easy. What is the nearest neighbor distance? And you know very well that 2R is the nearest neighbor distance. So, 2R is 2 times root 3A by 4 and that is nothing but root 3A by 2, that is all. Okay? So, this is your nearest neighbor distance. So, you have answer for everything, just a minute of calculation will get you the answer. Okay? So, knowing this R, now let us see, visualize and tell how to find the coordination number in body centered cubic crystal. Okay? So, now we are going to see the body centered cubic crystal. Can you see here an atom at the center of the unit cell, which is painted here in this model as red in color, because it has to be bit different from the atoms in the corners. So, atoms in the corners are given some other color, so that you can say, yes ma'am, corner atom I can see, and this is green in color. And an atom at the center face is nothing but, can you see this body diagonals also? Yes, 3 body diagonals are there, isn't it? So, they are all painted with yellow, so that you can see this body diagonal. But in model it is very difficult to make a big sphere and making these atoms to touch each other, but we can draw it easily, isn't it? So, in models making this big sphere and making it touching each other is bit difficult. Okay? So, it has been made as a small spheres. Okay? So, these 3 atoms are now I have drawn here. Yes? So, the one, can you see here? The one at this corner is this atom, and the one in the front down, and that is this atom, and the one at the center I have drawn here. Okay? So, this body centered cubic crystal has got how many atoms? It has got 8 atoms in the corners and 1 at the center. So, what are the number of atoms belonging to this unit cell? How will you calculate it? What is the corner atom contribution? This we have seen it in simple cubic crystal itself. Yes, each corner atom contributes only 1/8 to this unit cell. So, how many atoms are there like that? 8. So, corner atoms contribution is 1/8 into 8. Apart from that, you have only 1 atom present at the center. So, the number of atoms belonging to this BCC unit cell is, so let me write down that. So, number of atoms belonging to unit cell equal to 1/8 into 8 corner atoms plus 1 center atom. So, 1/8 into 8 gives you 1 corner atom and 1 center atom. So, totally how many atoms? Yes, 2 atoms are belonging to this unit cell. Okay. So, with this information, let us move on to one more, and what is that? That is coordination number. What is coordination number? The number of nearest equidistant neighbors. Okay. So, this atom is in touch with, I told you, these 2. At the same time, this is in touch with these 2. At the same time, this center atom is in touch with these 2 also. So, number of nearest equidistant neighbors for this center atom is 8. So, the coordination number for this body centered cubic crystal system is 8. Moving on to atomic packing factor. Let us calculate atomic packing factor. So, I have told you already what is atomic packing factor. It is the volume of number of atoms in the unit cell to the volume of the unit cell. So, the volume of the unit cell is A cube. How many atoms are there in this BCC? So, 2 atoms into 4/3 pi r cube. So, that is the formula for this atomic packing factor. Now, 4r equal to root 3a and r equal to root 3a by 4. This we saw just now. So, substituting that, 2 into 4/3 pi instead of r cube, I am going to put root 3a by 4 the whole cube by a cube. So, doing this simplification, you get this value to be 0.62 or 62%. Doing this simplification, we get the value to be 0.68 or 68%. Okay? So, this atomic packing factor is 68%. That shows that this body centered cubic crystal system is bit densely packed than simple cubic crystal system. You have many metallic crystals, iron, all have this body centered cubic crystal system. Let us try to learn some more in our next series. Thank you.